So today we will discuss about the adsorption process. As you can see here, a diagram in which a solution is present, adsorbent is present, and after the interaction of that solution and adsorbent, we get a clear solution. So the clear solution after adsorption we are getting, we want to see that what happened during adsorption that we are getting a clear solution. So we will start with the definition of adsorption, in which we'll explain that it is a process in which molecules become attached to the surface of a solid adsorbent. That adsorbate the molecules can be any gas, any contaminant, or any heavy metal present in water, any contaminant we can say. It can be a vapor. So what happens during adsorption? These contaminant or gas or any vapor attaches on the surface of solid adsorbent. And this can be happen using physical adsorption or chemical adsorption. Talking about the physical adsorption in detail, what happens in physical adsorption, physical bond between adsorbent and adsorbate are formed. Like there must be a weak interaction, like van der Waals forces are developed. But for chemical adsorption, a chemical bond is formed, which is stronger bond. So you can see the example here: hydrogen sulfide and iron oxides. After the reaction, after the chemical bonding, we are getting this Fe2O3, Fe2S3 and H2O, the water molecule. So here it is mentioned that heat of adsorption is low in physical adsorption and high in chemical adsorption. You can see from here that heat is released. So adsorption is the exothermic process. Like if I give an example, a vapor is attached on the surface of solid surface, and then we are usually going through high temperature to a low temperature, just like condensation, so that a certain amount of heat is removed in order to attach on the surface. So whenever adsorption phenomena occurs, there is release of heat. So that heat is called as heat of adsorption. So we are familiar with the terms now, that what is physical adsorption? Due to physical bonding, weak interaction, van der Waals forces develop. For chemical adsorption, chemical bonding, strong interaction, more heat is released. So we are familiar with these terms. Now we'll proceed with the application of adsorption at bigger, like industrial level. Just like here it is mentioned, for water treatment plant, we have an adsorption column. The water is coming inside, there is some interaction, and we are getting treated water. There was untreated water entering in the column. The filter media here is an adsorbent. So if we see this thing here in detail, the surface interface here, there should be any kind of interaction, or there should be physis option or chemis option. The contaminants present in the water adsorbed on the surface of adsorbent physically, or there should be some binding sites present on the surface of adsorbent that trap the contaminants, that did bonding with the contaminants. So There are different types of adsorbent. That's why there you see different phenomena. So why not talk about the adsorbents categories? Adsorbent for adsorption process, we have different adsorbents like zeolites, oxides and hydroxides, carbon based, metal organic frameworks, and clays. Each of the category has its own specialty. Zeolites are a class of naturally occurring synthetically produced crystalline aluminum silicate minerals, and they are used in adsorption process because of their surface area and other qualities. But oxide and hydroxides has a specialty of oxygen ions present, and this oxygen containing groups helps in binding with many metals. Like they can be used for removal of heavy metals from water. Carbon based compounds are used has very wide range because they have very good porosity that is needed for adsorption process. Metal organic frameworks are also versatile compounds. Like we have organic ligands, and they have also been used in separation applications. And clay is the cheap one, and because they're composed of hydrated aluminum silicates, and they have a good surface area. So each has its own speciality. If we talk about other aspect, then there are two different types of adsorbent: non-polar and polar. Like non-polar will help um, in removing non-polar contaminants, and polar will help in removing polar contaminants. Like for non-polar, we'll talk about in detail like toluene, benzene, some organic compounds, some non-polar organic molecules. And for polar, we have water, hydrogen sulfide, ammonia. So each adsorbent has its own specialty. Now we'll talk about activated carbon in detail because it has a very vast and wide applications in many separation processes. It can be used for water treatment, and it can be used for gas separation, also for CO2 removal and CH4, mostly for C6H6 for benzene and toluene. So there are many categories, there are many applications, there are many fields in which we can use activated carbon. So how it is produced? First we will see this. Activated carbon is usually produced by using cryogenic decomposition. Uh, we get activated carbon from coal, wood, shell, nuts, any component we can use, and it is activated by steam. And why we activate it? To develop porosity. We develop porosity to achieve high surface area. See? So we also have chemically activated that can be used for many other applications. You will understand this process by applying a numerical problem. Let's say we have an example here. The gas mixture of refrigerated condenser on a benzene tank on a benzene tank vent is to be passed through a bed of activated carbon to ensure that the vent is less than the legislative limit of 5 mg per meter cube at STP, standard temperature and pressure. Gas stream flow rate is given, concentration of benzene is given, partial pressure of benzene is given, temperature is given. So we'll start with the part A. Estimate the benzene mass of benzene in grams that can be adsorbed by 1 gram of carbon. So first we will understand the question. The question is saying that there is a condenser and the gas is coming out of the condenser to the adsorption column. Okay. And here after it passes through activated carbon, we have activated carbon here as a medium. You see? And we are treating a gas and at the end we are getting treated gas. And we have a mixed gas here. Flow rate is 0.113 meter cube per second. And the concentration of benzene is 204 gram per meter cube. The partial pressure temperature is also given here. So the gas is coming off the condenser and the temperature of after condensing is 10 degree. Now we will read the graph to estimate the quantity adsorbed. So the graph reading is not given for 10 degree. We will just plot a line here for 10 degree. See, I have plotted a line for 10 degree. Suppose we want to know what amount is adsorbed at the pressure of partial pressure of 46 milligram per gram. So we'll convert that partial pressure that is given here to what we have in the graph so that we will get the same value. We will take a log and we will get a value of now we will plot a line here around 1.66. And if I change the color, we are getting around 118. The unit is cc per gram. So we have got 118 cc per gram is equal to 118 centimeter cube per gram. So now we will convert the mass, that concentration to mass, by using standard temperature pressure condition. We know that at SPB, what is the volume of gas? It's 22.4 liter per mole. This is general information using PV is equal to nRT. So mass of benzene is equal to 118 centimeter cube per gram of carbon into, we will just convert the liter to centimeter cube just for the unit cancellation, and will multiply with the molar mass of benzene. You want to know this term come from? We know that C6H6 is benzene, and here 12 into 1 plus 1 into 6, so is 6 here. It is 78. Now we will get a value of 0.4115 gram of benzene per gram of carbon, because I was already given in the question that 1 gram of carbon, so it's here. Now we will proceed with the part 2. Estimate the bed size assuming a cycle time of 2 hours. Minimum is usually 1.5 hours. Okay. Regeneration after every fill. Assume a bed depth of 1 meter. So we are assuming that the adsorption column bed depth is to be, we have activated carbon here. Assuming the bed depth to be 1 meter. And carbon bulk density is 450 kg per meter cube. So to proceed with this, we will first start with the mass flow rate of benzene. That is concentration into volumetric flow rate. They both are given already. So mass flow rate is calculated, but we need to calculate total mass. So we will just divide with the multiply with the time. So time here is given to hours. So time here per cycle, this is cycle time. 2 hours is equal to 7200 seconds. So 23.052 gram per second multiplied by 7200 seconds. Second cancels and gives us 165,974.4 grams of benzene per cycle. And we will use this mass to convert it into, to calculate carbon mass. What we will do, we will just use the values from part A. Because how much benzene was adsorbed per gram of carbon? So we will use that relation. And we are getting value of 9.98 gram carbon. So that mass of carbon can be converted into volume. So volume is equal to mass over density. So we will use the value volume is equal to density over mass. We are given with the density value. That was the minimum mass of carbon required. But for exact calculations, we will use the rule of thumb that that it multiplies with one or with at least 3. That is a rule of thumb. Let me explain here. What is a rule of thumb? That it is a multiple of 3. That usually to ensure there is no drop in efficiency, we usually fix 3 times above the amount. So minimum or required value. So 3 into any mass amount. That is a rule of thumb for the adsorption column. So we are using that mass here, the maximum that should be here. So this is the volume of carbon that should be used. And if we convert that volume into height, sorry, we are given with the height as well. We have 1 meter height, but to the diameter. Then we have value of V and H. We will just calculate the value of R, that is 0.9252 meter. So this is the radius and this is the diameter. This is for carbon. This much amount needs to be filled in the carbon. Okay, now we will calculate the percentage of adsorbed vapor that would be recovered from the bed by passing steam at 1.4 bar and a temperature of 200 degrees C through the bed until the partial pressure in the exit stream is reduced to 10 millimeter mercury. What we are given? We are giving temperature of 200 degrees C and pressure of 1.4 bar. Can we convert that pressure into millimeter mercury? But we don't need that because reduced pressure is already given of 10 millimeter mercury. So we'll just take the log and it is 1. So at 1, we will just plot the graph at 200 degrees C, which is around here, and at 1. I should use another color so that you can better see the line. I have messed the condition here, so it's okay. 1 temperature, and it is around 20. So concentration of benzene here at this condition is 20 centimeter cube per gram. So why I have calculated this amount? Because we need to calculate the percentage of adsorbed vapor. We need to see the what is the percentage of vapors recovered. So we will just do initial minus final. That's how we will calculate the recovery. The initial value we calculated already, it was 118. So 118 minus 20 over 118 gives into 100 gives us a value of 83.1%. So what's the next question? Calculate the residual pressure and concentration of benzene in the gas mixture treated with regenerated carbon from part C after cooling at 200 degrees. In this adequate to meet. Okay. So we need to know that the amount of carbon is sufficient to meet the legislative limit. What we see here, that the regenerated carbon is cooled down. After regeneration, the carbon temperature is cooled down to 10 degrees C. Now we will see that what's the pressure here. Because we have temperature and we already know the pressure value, we can the amount of carbon after reduction. So that was calculated here, the 20 centimeters, so 20 centimeter cube per gram. So we will plot a line for 10 degree here, and we have 20. So we are getting the amount around minus 3.6. So at the given condition here, we will calculate from graph we will just take the log and we will get the value 0.0000251 gram millimeter. I don't know why I'm speaking about the gram again and again. It's millimeter mercury. And if we will convert it to ATM, we will just multiply with 1 ATM is equal to 760 millimeter mercury. Because we will use the values in ATM later, that's why the conversion is being done here. Otherwise, not needed if you are required the values in millimeter mercury. So basically we need to see that if the amount of carbon is sufficient or not. So we need to convert this into mass. So we will use Raoult's law, which is mole fraction of benzene into total pressure is equal to saturated pressure plus pressure. So now we will put the values. We shall proceed here. So we already calculated the value in ATM. Now convert that fraction to mass. So for mass of benzene, we will multiply with the volume at STP into molar mass. Writing units is very important. Otherwise, you will not get the right. You may do it wrong because while you're writing the units, you do cancellation. That helps in calculating the right unit. So I'm getting 1.151 into 10 raised to minus 3 gram of benzene per meter cube of gas. So the legislative limit is 5 milligram per meter cube. So it is equal to 1.151 milligram per meter cube. 1.151 milligram per meter cube is less than 5 milligram per meter cube. So the amount of carbon is sufficient because it is less than legislative limit. So we have done numerical, we have done we have gone through in detail that how we calculate the diameter, the mass, the concentration, all the requirements for adsorption column because adsorption happens there. So I hope it is clear